In this video, we will look at several applications of the derivative, mostly focusing on rates of change in physics, so position, velocity, and acceleration, and biology, looking at population growth. We will show how to estimate values of a new value of a quantity from an old value if we know the amount of change. We'll talk about the difference between average rate of change and instantaneous rate of change, which we've already talked about a little bit. Again, we'll apply these rates of change to displacement, position, like change in position, velocity, and acceleration for objects moving on a straight line. And we'll use, like we said, almost the same as example, or objective 1, predict future population from present value with population growth rate. And actually, although there is this objective in this section in the book, we are not going to look at the business applications. We are assuming that most of our business majors are taking a different calculus class at Inver Hills, so we're focusing more on the physics and biology applications. So one of the equations or ideas we're going to be using in this section is that if we are changing our input, which in most of our applications is going to be time, by a small quantity, we can approximate the change in the function value or the output or the population growth, for example, by taking the original function value multiplied by the derivative or the rate of change at that given time times the amount of time that we're incrementing by. So again, you want to remember that the derivative is a rate of change. At a given moment, and then f of a would be actually that function value. Right? And so we want to think about, well, why would this be true, that we can estimate the new function value by taking the old function value and the derivative at that point times h. And so let's think about a little sketch. Maybe here's my point A, and then if that's A, f of a is here on the y-axis. And if I change a little bit, I add a small quantity h, the distance between these. So if I increase a little bit, f of a plus h will be right on that curve. But what we're trying to do, instead of using f of a plus h, we're saying we could approximate that by taking f of a, which was this y value, and adding to it the derivative times h. Right? Remember, derivative is change in y over change in x, and h is also a change in x. So if I multiply the change in y over the change in x times a small change in x, I'm going to end up with a change in y. Right? And it would be the change in y that I get by moving along that tangent line. Right? So when I put these pieces together, the y-coordinate that I would approximate from this picture would be the original y-coordinate plus the slope times that small change in x. So we can see that, at least in this figure, as long as we're close to the point of tangency, the function value and the value along the tangent line are about the same thing. Right? So what we're saying is the function value itself is going to be about the same as if I move along the tangent line, move a distance of h away in the x direction, and then move up whatever I would move up along the tangent line if I am moving a change in h in the x direction. So if I want to use that idea in example 1, I'm given f of 7 is 3 and f prime at 7 is -2. And I want to use that to estimate f of 7.3 and f of 6.8. Right? Notice that 7.3 and 6.8 are both close to the anchor point that we have, which was 7. If they were asking us to estimate, f of 20, it wouldn't make any sense. This is really only useful for values that are close to our anchor point, in this case 7, right? So we can just look at the formula and we can say f of 7.3, that's the same as f of 7 plus 0.3. So 0.3 would be the h in this case. And the formula says that's about the same as f of 7, the function value at our anchor point, plus the derivative at our anchor point, times whatever the change in x was. And the change in x to move from 7 to 7.3 would be 0.3. So putting these pieces together, that would say, okay, f of 7 was 3, f prime of 7 is negative 2, and then we'll multiply that by 0.3, so we'll end up actually moving down 0.6. So our approximation would be 2.4. Let's make a sketch and see why this makes sense. Okay, so we're told that f of 7 is 3. So we have this point on our function, and we also know that the tangent line to the function at x equals 7 has slope negative 2. So if I move back 1, I'm going to go up 2, and if I move to the right 1, I'm going to go down 2. So this would be the tangent line to the graph of f at that anchor point 7, 3. And so I can see if I move ahead a little bit to 7.3, the tangent line is going to drop, right? The y values on the tangent line are going to drop, and they would drop by 0.6. So our approximation to the function would be, that's about 2.4. And again, the function itself might not be exactly there. It might, do something like this, but the y value that we're going to get is going to be close to 2.4. Similarly, f of 6.8, we could say, well, 6.8 is close to 7. It is 7 plus negative 0.2. So this time our h value is 0.2. And last time I should have mentioned this, that h value was 0.3. I probably mentioned it, but didn't write it. So the formula would say, well, this is going to be approximately the same as the function value at 7, which we already had was 3, plus the derivative at 7, this time times negative 0.2, because we're stepping back in the x direction. So we would, just from our picture, we would anticipate that this value should be higher than 3. Let's see what we get. So we'd have 3 plus negative 2 from the slope times negative 0.2. So here we're getting 3 plus 0.4. So we would say the function value is approximately 3.4. It won't necessarily be exactly 3.4 unless the function is linear. We don't know. But it will be close to, how did I write 3.3? 3.4. So knowing one function value and the rate of change at that function value, we can estimate or approximate values for the function that are close by, right? And this is the idea we'll be using when we try to estimate population growth, looking ahead to the future. But for now, we'll look at velocity and speed and acceleration and some examples involving these things. So if s of t is a position function, the velocity, that would be the rate of change of the position, is the first derivative of the position function. And the speed, we want to be careful, is actually not the same as the velocity. It's almost the same as the velocity, but it does not include a negative sign ever. So the speed doesn't give us any information about direction. It's just the absolute value of the velocity, right? So velocity the sign of the velocity indicates direction. So the speed doesn't give us any information about the direction, it just tells us the rate of motion, not the direction. And acceleration is the rate of change of velocity, so the derivative of velocity, which then would be the second derivative of position. So let's take a look at example 2. It says a penny is dropped from a height of 128 feet. Its height above ground t seconds later is given by s of t equals negative 16 t squared plus 128. And question A says, what is the instantaneous velocity? And same as velocity. Anytime someone says velocity, they're implying instantaneous velocity of the penny when it hits the ground, right? So this is a little bit more complicated than a problem that just says, what's the velocity at 2 seconds? They're not giving us directly a time, they're giving it the time to us indirectly instead. So we'd be thinking, when it hits the ground, that's when the position is 0. And we want to find t, and use that t to find the velocity at the right time. So when it hits the ground, we are going to need to do a little bit of work to determine the t value. This would give me 16t squared equals 128. 128 divided by 16, that must be 8. So then t would be positive or negative square root of 8. And it doesn't make sense to be looking backward in time for this, so we'll just say t is positive square root of 8. Right, so that's our first step, is find the time we need to use. And then we'll find the velocity function for any time, and then we'll fill in this specific time. So v of t would be negative 16 times the derivative of t squared, so times 2t, plus the derivative of 128, which would be 0. And we can reduce this, not reduce, but simplify this to negative 32t. And the label would be feet per second, because the height was in feet and the time was in seconds. So v of t would be negative 32 feet per second. And so we want v at v at square root of 8. So negative 32 times the square root of 8 feet per second. If you want to clean that up, square root of 8 is the same as 2 times the square root of 2, so we could say negative 64 times the square root of 2 feet per second. So that's the instantaneous velocity, the velocity at an instant when it's hitting the ground. So we find the t and we plug that in. And then the next question says, what's the average velocity? And for that, we want the change in position over the change in time over the interval from 0 to square root of 8. So we want v average. The pattern is s of b minus s of a divided by b minus a. And in this case, a is 0, the starting time, and b would be square root of 8. So s of b would be, no, that was fine. I was going to say we need to make this negative. I don't know why I keep wanting to make that negative. The velocity is negative, but not the time. So the velocity at the end point was negative 64 times the square root of 2. And the velocity at the start would just be 0, right? If I do v of 0, I get negative 32 times 0, which makes sense because it says the penny was dropped rather than thrown down. So s of a would be 0, and then b minus a is square root of 8 minus 0. And we just said square root of 8, that's the same thing as 2 times the square root of 2. So we have negative 64 over 2, so it looks like negative 32 feet per second was the average velocity on the fall from the start to when it hits the ground. Right? So a little bit, not the same as the instantaneous velocity right at the end. We're just looking at the average velocity over that whole interval. All right, then the position function here gives a position in miles of a freight train where east is the positive direction and t is measured in hours. And we're asked first to figure out the direction the train is moving when s of t is 0. Anytime we're asked about direction of motion, that's asking for the sign of the velocity. So, and again, it's kind of like the last one. We're not told at a specific time. We're told when this position is 0. So here, it's not a height. We're moving east and west instead of up and down. But so when the position is 0, we need to find those t values and use those in the velocity to determine the direction. So s of t is t cubed minus 8t. That's going to be 0. If we want to, we need to factor this. So 0 equals t we could factor out, and then t squared minus 8. So it looks like either t is 0 or t is positive or negative square root of 8 again. And I think once again, let's assume that we have a starting time of 0. So let's assume t greater than or equal to 0 only here. So just we'll use t equals square root of 8, not negative square root of 8. And so we need the velocity function in general, and then we want to compute the velocity at these two times. So v of t would be 3t squared minus 8, just doing the derivative of position. And so the velocity at 0 would be, throwing in t equals 0 into my velocity, it looks like negative 8 miles per hour, since position was in miles and time was in hours. And v at square root of 8, when I fill that in for t, I'll have 3 times 8 minus 8. So 24 minus 8, so 16 miles per hour. So our conclusion would be, it said, let's see, east is the positive direction. So at time 0, train was moving west because we have a negative velocity. At time square root of 8 hours, the train was moving east. Right, so we just took the sign and the velocity at those two times when the position was 0, and we found, since one of the velocities had a negative sign, that's whatever would be the negative direction, and then whichever velocity has a positive sign, that tells us the train is moving in the positive direction. And we are told east is positive in this orientation. In part B, we're asked to find the direction the train is moving when a of t, the acceleration, is 0. So again, we want to figure out the direction. That would be the sign of v of t when a of t is 0. So let's start by finding a of t. And we remember that a of t is the derivative of v, so we want 3 times the derivative of t squared, which would be 3 times 2t, so 6t, minus the derivative of 8, which would be 0. So a of t is 6t. That means that a of t will be 0 when 6t is 0, and that would clearly be when t is 0. So Turns out that's one of the times that the train was actually having position 0, right? We already saw t equals 0 in part 1, and we already saw that v of 0 is, what did we get? -8. So train is traveling, that was west, when the acceleration is 0. Now we're trying to find the time intervals when the train is slowing down or speeding up. So now what we want to actually analyze is, let's look at the graph of speed. And remember that the speed is the same thing as the absolute value of the velocity. So if we think about the velocity graph, and we're just going to think again about time greater than or equal to 0. The velocity was a parabolic function, and it would be shifted just down 8. So the vertex will be down here at -8. And let's see, the velocity is going to be 0 when t is, what, positive or negative square root of 8/3. Let's find that. When is v of t equal to 0? That would be 3t squared minus 8 equals 0. So t squared is 8/3. So t is positive or negative square root of 8/3. And we're just going to consider positive times, so we'll just look at that one. So here's where the velocity hits 0. We could clean that up, but let's just leave it as square root of 8/3. So that's a graph of v of t. And if I want to show the absolute value of that graph, what I think about is anything that is negative currently, any y value that is negative, when I take its absolute value, it will be the same distance away from 0, but on the other side of the x-axis. So the absolute value graph moves all of the negative values and makes them positive, and then leaves the positive values where they were. So the red graph here, this would be the absolute value of v of t, or the speed. So if we're thinking about this as our graph that shows the speed, we can see the graph, or the particle, or what are we talking about? A train. The train is slowing down on the interval from 0 to square root of 8/3 because it's coming to a stop on that interval. We're losing speed. And then it comes to a stop at the square root of 8/3, and then picks up speed after that. Right? Because the absolute value of the velocity is decreasing for the time interval from 0 to square root of 8/3, and then it's increasing for the time interval after square root of 8/3. So if we think about the absolute value of the velocity, that gives us an idea of when the train is slowing down or speeding up. On example 4, instead of being given a formula, we have a picture of the position, right? So we've got this object that's moving along a straight line, and we're tracking its distance from whatever we've labeled as point 0 as we go along. So we think of x as like our time, and y is the distance away from 0. I should be a little more careful because it's actually the signed distance away. Looks like y could be negative, in which case we would just be talking about on the other side of 0. So we're told or asked to use the graph of the position function to determine the time intervals when the velocity is positive, negative, or zero, right? So remember, velocity positive would mean position moving or particle moving in the positive direction. V of t equaling 0 would mean not moving, and V of t less than 0 would mean moving in the negative direction. So for this particular particle or object moving along a straight line, velocity is positive. Let's see, on this stretch here where we're moving in the positive direction, and then we turn around and then we stay in place, and then we move backward a little bit further, and then we begin moving in the positive direction again. So V of t greater than 0 would be what I just kind of highlighted in green. So it looks like t between 0 and maybe 1.5. And also t between 6 and 7. Then we want to know when the velocity is negative. So velocity negative means we're moving in the negative direction. So we've turned around. So that would be here on this little stretch between 1.5 and 2. And then we're staying in place for a while, and then we move further in toward the negative direction, back towards 0, between 5 and 6. So that appears to be, let's say, from 1.5 to 2, and from 5 to 6. And then while there are some instance where the velocity is 0, they're asking us for actual intervals when the velocity is 0. So that would be this little stretch in the middle where we see no change in position. So here we would want, oops, not that. This little stretch here where we see the position isn't changing on that time interval would continue to be 2 units away from the point we've labeled as 0. So we would say the interval for the stopped motion would be from 2 seconds, or whatever our time unit is here, to, it looks like, 5. And then we're asked to sketch a graph of the velocity function. And I think I'm going to try to sketch the graph of the velocity function right on top of the function, the position function that's given. So I can see that when the particle turns around, or the object turns around, so right at this high point, the velocity should be 0, because it was moving in the positive direction and then turns around, so stops for that instant, and then continues to move in the negative direction, or begins to move in the negative direction. And I can see, well, this looks like a quadratic function, so I'm going to make the derivative, the velocity is the derivative of position, I'm going to make that a linear function. And it seems like I would want something that's linear, with starting with positive values, getting to 0, and then switching to negative values. So I would want something that's linear, but with negative slope. Right at that peak, again, that's where I should be at 0. And then I have this corner where something strange is going on, right? I have an abrupt change in position. It's like I have a sudden stop. And at a corner like that, we know the derivative is not defined. So when I get to 2, where that corner is, I want to make sure I have an open circle here. And then I would say, well, now my velocity is 0 for a stretch. I'll make another open circle at the point 2, 0, and at the end of that interval, an open circle at 5, 0, and I'll connect those. And then I can see I have another branch here from the velocity. The velocity starts out negative and then crosses 0 and then becomes positive. And again, this position function looks quadratic, so I'm going to make my velocity function linear. And it's hard to tell without doing, a lot of really digging into what points we have. But as long as you have something that looks linear and it's moving from below the x-axis to above the x-axis, that's good enough, right? We don't need to compute exactly what the slope should be. This is fine. And I guess I'll probably put open circles on the endpoints here since it's a strange abrupt stop. I wouldn't be picky about that either on a quiz, as long as you have 3 branches like this, 2 of them linear, the first one with negative slope and the other with positive slope, and then a horizontal with y value 0 in between. So that would be a sketch of the velocity function in blue there. And then it says use the graph of the velocity function to determine the time intervals when the acceleration is positive, negative, or 0. Right? And so what we want to remember is acceleration is the derivative of velocity. Right? So we would track the slope of the velocity graph. So let's see, on the stretch between 0 and 2 seconds, I can see that the velocity graph is linear with negative slope. And so the acceleration would be whatever that slope is, and that's clearly negative. On the stretch between 2 and 5, where the velocity is a constant and it's 0, the acceleration is just also 0 because the slope of that horizontal line is 0. And then on the stretch between 5 and 7, I can see that the velocity is a linear function with positive slope, and then that means the slope of that is, the acceleration is positive. Then in part D, we're asked to find the time intervals when the object is again speeding up or slowing down. So again, we can think about the graph of the absolute value of velocity, which I'm going to make red here. And remember, when we're doing the absolute value of a function, we would say, all right, anytime that function is positive, it stays the same. So this would stay the same, but here where the function drops negative, I will reflect it across the x-axis, and that would be what the speed looks like. And again, here we have a little stretch where the velocity is negative, so the speed would be reflected across the x-axis, and then we would continue along with the original velocity function between 6 and 7. And the speed would be 0 here where the velocity was 0. So that's now in red. And what we can see then is that the object is slowing down between 0 and 1.5 seconds. oh, I keep saying seconds, but there weren't really units given on the time here, but for t between 0 and 1.5, and also for t between 5 and 6. And speeding up for t between 1.5 and 2 and between 6 and 7. Right? So we approached this by looking at the graph of the absolute value of velocity. But another thing we can do is compare the signs of the acceleration and velocity. So I'm going to include this right in this space where I have a little gap here. You can check this. We can say slowing down is going to happen when the velocity and the acceleration have opposite signs. So one positive, one negative. And speeding up will happen when the velocity and the acceleration have the same sign. So for example, maybe the particle has a positive velocity and acceleration is positive. So it's already moving in the positive direction and moving in the positive direction at a faster rate. Or maybe the object is moving in the negative direction. So maybe it's moving at negative 5 feet per second. And then if acceleration is also negative, that means it's moving in at a more negative value, right? So it would be moving maybe from negative 5 feet per second to negative 7 feet per second, which would mean it's actually gaining speed even though a of t is negative. So it's a little bit strange, but this also works. If we can, we can analyze the graph of the speed, which is the absolute value of t, but we can also look to compare the signs of v and a. If they're opposite each other, then the particle is slowing down. If they are the same, then the particle is speeding up. Right? So that's just another tool we can use. Next, we'll move on to some examples that involve questions about population growth and estimating future population. So just a definition, if P of t is the number of entities present in a population, then the population growth rate of that population is defined to be the derivative of the population function. So in example 5, we are told the current population of a mosquito colony is known to be 3,000. So in symbols, that would mean P of 0 is 3,000. And we're told P prime of 0 is 100. So let's think about what that is telling us. The 0 there tells us at day 0. And the 100 is a growth rate. So we would say the population is growing at a rate of, we'll say growing because it's positive. If it were negative, we would say shrinking. And then we'll think about the label. The numerator label, it's always something per something else. The numerator label always comes from the original function whose derivative we're taking. In this case, that would be the mosquito population. So 100 mosquitoes. And then it's per, in this case, day, because time is measured in days. So 100 mosquitoes per day is the rate of growth, at least on day 0. Right? And that's the only information we have, right? We know the initial value and we know the rate of growth at the start. And we're asked to use that to estimate the size of the population in 3 days. So if you think back, this is very similar to what was going on in the first example we looked at in this section. And we used this formula that said f of a plus h is about the same as f of a plus f prime of a times h. Right? So here, instead of f, we have p, and we're trying to think of a formula for p of 3, but we know something about 0. So for us, the a value is going to be 0, and the h value is how far we are away from that anchor point, and that would, in this case, that's going to be 3. So we would say p of 0 plus 3 is about the same as p of 0, the starting value, plus the rate of change, p prime of 0, times the number of days away we're going to be, which is 3. Right? So this makes sense because we'll say, well, we started with 3,000 mosquitoes and we're gaining roughly 100 a day, and we're going 3 days out. So let's just think about the label here. This would be 3,000 mosquitoes, and 100 was mosquitoes per day, and 3 is days. So we've got 3,000 mosquitoes plus 300 mosquitoes. The labels match, and we should be able to add those values, and we'll get an approximation of, well, about 3,300 mosquitoes on day 3. Right? But you can kind of see what we're doing here with that, that same pattern that we are using on the first page of this section. The next one says the population of a city is doubling every 7 years, and the current population is 50,000. So for this one, we can say p of 0 is 50,000. We could also say, well, that means that p of 7 would be about 100,000. And we're asked to estimate, again, the population 3 years from now. So this is a similar situation to what we had last time. We want to find p of 3, or an estimation of it, and we know something about p of 0. So we'll say, well, p of 3, which we'll think of as 0 plus 3, would be about the same as p of 0 plus the derivative, or the rate of change at 0, times the h value that we want to move away from 0, so times 3 again. The p of 0 we have, the thing that's trickier on this one is they didn't just directly tell us p prime, we need to estimate it. So if we want to estimate p prime, we need a change in population over a change in time, right? Because usually we want a change in our outputs divided by our change in our inputs. So for this, to estimate p prime of 0, we want to find some information about change in population over change in time. And we can see, well, over 7 years, we are told that the population is going to double, which means it's going to change by 50,000, which we've got from 100,000 minus 50,000. So we would say, well, from the information that's given, we can say p prime of 0 is approximately 50,000 people per 7 years. And that's not going to come out even, so I'm just going to leave it as that. So we'll say p of 3 is going to be about equal to 50,000, the current population, plus the rate of change, 50,000 people every 7 years, times 3 years. Right? And so again, the label here, we've got people, And here we have people per year, and 3 is years. So the quantities we're adding are all labeled as people, so that's good. We want to add and get an approximation of the number of people. So for this, we'll probably need a calculator because it's not going to come out even. So we had 50,000 plus 50,000 over 7 times 3. So roughly 71,428. All right. Then example 7 says a small town in Ohio commissioned an actuarial firm to conduct a study that modeled the rate of change of the town's population. The study found that the population, measured in thousands of people, can be modeled by this function, where t is measured in years. So the actuarial firm gave them a formula for the population in t years, and we are asked to find the rate of change for this function. So here, p prime of t, we just want the derivative of p of t. So we'd have negative 1/3 constant multiple times the derivative of t cubed, which would be 3t squared, plus the derivative of 64t, that's linear, so the derivative is just 64, plus the derivative of 3,000, which would be 0. So we can clean that up, and we'll have negative t squared plus 64. And this would be thousands of people as the label per whatever the time interval was, per year. Because p is measured in thousands and t is measured in years. So when we do the rate of change, we'd have the change in thousands of people per year. So let's compute p prime of 1, 2, 3, and 4. P prime of 1 will have negative 1 plus 64, so 63. P prime of 2 will be negative 4 plus 64, so 60. P prime of 3 would be negative 9 plus 64, so 55. And then P prime of 4 would be negative 16 plus 64, so 48. Right? And these tell us, we can see that the rate of the population, because these are all positive, the population is growing each year by first 63,000 people per year, and then 60,000 people per year, and then 55,000 people per year, and then 48,000 people per year. But we can see it's growing by fewer people per year as time goes on. Right? So let's say because each of these values is positive, the population is growing each year. And let's say, for example, in year 3, growth rate is roughly 55,000 people per year. And then we can see, but the rate of growth appears to be slowing. At least for time between 1 and 4, which is what we're looking at. right? Because we grew by 63,000 people per year in year one, and then that dropped each year down to 48,000 people per year in year four. So then let's look at the second derivative. The second derivative at any value of t would be -1 times the derivative of t squared, so -2t, plus the derivative of 64, which is 0. And we can think the label for that would be the label for p prime and then divided by years. So thousands of people per year per year. So we're measuring the rate of change of the population growth. So it looks a little strange to write that, but that's exactly what it would be, thousands of people per year per year. And we can see p double prime at 1 would be -2, p double prime at 2 is -4, p double prime at 3 is -6, and p double prime at 4 is -8. Right? So we can see, since these values are all negative, we see that p prime of t, the rate of growth, is decreasing. So the population is growing, but at a slower pace each year. So we could say, although the population continues to grow, the rate of growth is decreasing over between years 1 and 4. So p double prime is telling us about the rate of change of the population rate of change. So at least we've seen some examples from physics and some examples from biology, but what you want to keep in mind is that the derivative of any function measures the rate of change of that function. That's what the derivative is doing.